Hi, everyone. Welcome to Yusra's talk today for the Applied Algebra seminar. She'll be talking to us about a gallery model for affine flag varieties. Just like last time, we'll have a 5-minute break in the middle. And yeah, so I'll let you take it over. Yeah.
Okay. Thank you very much, Aram, for giving me the chance to speak here. Thank you all for coming to my talk. We will be talking about a gallery model for affine flag varieties, and I'll try to say what both of these things are, and then what kind of questions we hope to answer with them, and then how we hope to answer them. So all of this is joint work with Liz Milicevic, Petra Schwer, and Anne Thomas. And our paper, if you would like to check it out for the details, is listed here. So the plan for today is to talk about Coxeter complexes and folded galleries so that I can say what I mean by a gallery model. Then talk about buildings and the affine flag varieties, and then talk about how these things connect via retractions, and then finally talk about shadows, which are sort of the key thing that I'm going to be asking questions about and trying to answer questions about. So let's get started. Okay, our main object, our central object, is going to be a Coxeter system. Can people see the laser pointer? I can see you guys nod if you're nodding and you have your video on, but also feel free to interrupt if anything's ever difficult and just unmute yourself. Okay, so we're starting with the Coxeter system, which is, roughly a Weil group or Coxeter group with some specific set of generators S. And for this talk, I'm going to be thinking of all of my Coxeter systems in terms of a Coxeter complex. A Coxeter complex is an n-1 dimensional simplex where n is the size of my generating set. And my top dimensional simplices I'll call alcoves. Sometimes I'll call them chambers. These two things mean, I'll try to stick to alcoves, which is more common for the affine setting we'll be in, but these are sometimes called chambers as well. I have one alcove for every element in my Coxeter group. So every element here is going to be associated with the top dimensional simplex. And the way I decide when two of these simplices are adjacent is based on whether I can get from one to the other by right multiplying by a generator. So if I have W and WS, these are going to be adjacent along a wall, a codimension 1 face that is going to be labeled by the generator. And this is how I'm going to visualize all my Coxeter groups. And so here are some examples. These are sort of important examples to keep in mind. In the finite case, if I have my type A2 Coxeter group, and here's the associated Coxeter diagram, we're used to thinking of those. This has two generators, S1 and S2. And so my red panels are going to lead me to something where I multiply on the right by S1, and my blue panels lead me to multiply on the right by S2, and because all of these generators have order 2, it really is a symmetric relation here. And I could do this in higher rank, and then I have, higher dimension simplices. So here my top dimension simplex is 1, here my top dimension simplex is 2, and I have 3 different kinds of walls with 3 different kinds of generators. Yes, so here are some nice finite examples. This example is going to be especially important for us, this little hexagon, so we'll see it later. And because I want to have one element for everything in the Weil group, I should point out that the relations are captured by closing up the adjacency and forming loops over here. In the affine case, I have these tessellations of Euclidean space. Because I have these nice infinite Coxeter groups over here with generators that have me fill out a plane or an infinite line or something like this. So in this first example here of an affine Coxeter group, my Coxeter complex is going to look like a plane. My top dimensional simplices are going to be 2-dimensional and they have 3 faces. I still have the kinds of relations that I had before when I just look at S1 and S2, because if I look at the subsystem S1 and S2, I'm back in the finite case I was looking at before. So this is my little familiar hexagon finite picture that I had. But now I also have S0 that takes me in a different direction. And I can label every single one of these triangles with an element in my Coxeter group. So if I went out to this simplex over here, because I'm crossing a blue panel over here, I know that I'm going to right multiply by S2. So this element would be S0, S1, S2. And I can similarly label everything, right? But this is how I'm going to think of my Coxeter systems in terms of these Coxeter complexes. So these are two nice sort of rank 2 examples to keep in mind. Here is another important example to keep in mind where I just have this infinite line. I have one-dimensional simplices, and this is my infinite dihedral group. I just move further and further out. Okay, so this is sort of the starting thing that I'm looking at. And within these Coxeter complexes, I want to define a gallery. So a combinatorial gallery is a sequence of alternating panels and alcoves where these blue things at the end are sort of optionally included, but formally they should be there. And I'm going to have every panel that I'm sort of interspersing with living on both of the alcoves on either side. So the way I think about a panel is I start someplace and travel outwards. And so it's a gallery because I can think of this as walking through the alcoves. And I'm going to keep recording what kinds of panels I cross and what kinds of chambers I end back up in. So over here, if I get rid of the original optional sort of panels, I would have well, actually, let me not record all of these things over here. Let me just write over here that the alcoves I'm crossing are S0, then I have S0, S1, and then I have S0, S1, S0, and I can label these pretty fast because I'm just right multiplying by the generator that goes with the color that I've crossed. My last thing would be S0, S1, S0, S2. And in between, the panels that I have are of type 0, type 1, type 0, and type 2. I want to keep track of the type of each of these galleries by recording what each of these panels are. And now you might be thinking to yourself that there's a lot of redundancy of information here because every time I cross a panel, I'm right multiplying, and so I should know what the next chamber is. But eventually what I want to be able to do is come backwards and fold also. And then it really does become important to think about which panel I bounced off of and which chambers, whether I crossed my alcove or, so whether I crossed into a new alcove or returned to the old alcove that I started at. So far so good, I hope. Feel free to contradict that. Combinatorial gallery, I'll say, is folded at panel I if the chamber before it and the chamber after it are the same. So I come in to this panel from some alcove and I leave through the same alcove. And here I am doing this thing where I'm going back and forth between chambers and alcoves. And it is because both these terms are used. Apologize for that. But this is, yes, called folded if I go back through the same chamber on either side of this panel. And now I want to talk about what kinds of folds I want to allow in my system. And for that, I need to define an orientation. So an orientation phi is a map that assigns plus or minus 1 to each panel and alcove pair. So if I have a panel P over here and an alcove C, then this side I could give a +1 to. If I have in the same panel, but another alcove, this is really a different pair, and then I could give it a different value. I could give it -1. I could also give it +1. There's nothing here that's keeping me from just putting pluses everywhere. But that's a trivial orientation, and it's not going to be very interesting for us. We're going to be looking at locally non-trivial orientations where if one side has a plus, the other side has a minus. But remember that this assignment is really made to the panel and alcove pair. And once I have this, I would say that my combinatorial gallery is positively folded if I, first of all, have a fold. It's positively folded at PI if I have a fold and that fold is on a positive side. So this here is positively folded. Positively folded. And if I come from the other side, this here is negatively folded. And I should say at PI, going back to here, this is positively folded at PI. And so in general, a positively folded gallery would be something that only has positive folds or no folds at every panel, but leaves out negative folds. A negatively folded gallery would be unfolded or have negative folds at every panel, but leaves out the case of positively folded, Right, so these are the galleries that I'll be looking at. And now I'm going to sort of shift gears and talk about where these folded galleries might come from, why it makes sense to look at these folded things. And I'm going to do this by detouring through talking about sort of a larger simplicial complex, but also talking about my affine varieties. And then we'll bring all of these together. So this is the gallery half of this. Now going to the second section of the talk, I want to define a building. And there's a lot of writing there, which I hope you will not frantically try to read, but just let me explain it through example. The formal definition is there in case you would like it completely. But basically, a building is a generalization of a Coxeter complex. It's made up of a union of Coxeter complexes. So in this case, I have a union of those hexagons. There's lots of different hexagons if you trace it out in different ways with the alternating red and blue vertices. I've sort of mushed them in together, but there's a method to how I've folded them all in together. And this is basically following these two principles, B1 and B2 up here, which says that anytime I have two simplices, X and Y, there is a common apartment, a common Coxeter complex that they both live on. So in this case, here I have a common hexagon that both this X and Y are on. Or I could look at another pair, so I could look at something like A and B, and then I would have another hexagon that A and B live on. And this one sort of comes out this other way. But anytime I pick up two simplices, I can find a common Coxeter complex that they live on over here. And you could try this out combining A and Y or A and X. There definitely is one there. Maybe it's twisted around, but this alternating edge, red dot, edge, blue dot, and so on we have. And then the other thing that I need is that if I have two apartments that contain X and Y. So let me give you another example of something that contains X and Y. Let's see if I can highlight another hexagon. So here's another hexagon that contains X and Y. And anytime I have two apartments that contain the same simplices, there's an isomorphism from one to the other that fixes the intersection pointwise. So I could fix this over here, and then my isomorphism would consist of taking this edge to this edge to this edge, and finally this one to this over here. Essentially what I've done is I've put my hands at X and Y and then smoothed out over the hexagon and thought about where these edges collapse. And I can do the same thing on this side. If I have X and Y, then I could look at this sort of infinite line. I want a copy of a Coxeter complex, and we've already seen that infinite line example. I could take another copy over here, and these ones would both map onto each other. There's an easy isomorphism from one infinite line to the other by just collapsing one of these down as it branches further and further out. So both of these are basically like my previous pictures that I've drawn of Coxeter complexes, but with lots of branching at every panel. If you want to see a higher rank version of this, then basically I can't draw a full thing, but instead of having two triangles living along a common edge, I'd have sort of more flappiness over there and just have this leaf out like a book. So far so good, I hope. Okay, so here I have a building. And the reason for looking at buildings is because these sort of arise naturally in the study of algebraic groups. That's the origin of the subject. Some of you might be very, very familiar with these, but this is assuming you're not. So buildings, they come up quite naturally in the study of algebraic groups. And I'm not going to write out the full correspondence, but here are sort of examples that lead to the two pictures that we have before, and also sort of indicate why it is we see these Coxeter complexes and where the Coxeter groups come in. So if I have a reductive group over the field with two elements over here, I can look at a Borel subgroup, which for our example is just the upper triangular matrices. G mod B is what I would call my flag variety, which I'm not going to explain further if you're not familiar with this, but I'm really looking at cosets of B. And so in my building, every edge is going to correspond to one of the cosets of B. And G in this case has a very nice decomposition, the Bruja decomposition, where it is the disjoint union of these Bruja cells which have the form BWB, where B is something in my Borel subgroup, W is an element in a Coxeter group, and then B is the thing that I was quotienting out by in the first place. W in this example is going to be my type A2 thing here, so W is going to have this diagram in this case. And so when I look at how this, how the cosets of B look over here, well, I'm going to put down an edge for each of these, and then I'm going to have this be adjacent if I get it by multiplying by something in my Coxeter group. So here I have S1, which is a permutation of the first two elements. S2 would be a permutation of the other two elements. And I have a little bit more branching than I would in just an ordinary Coxeter complex, because I can also multiply by something in B and get a new element in this same cell. Now, because I'm looking at F2, and this is a very simple example, there's only one other sort of coset of B that I need to worry about, that is something times S1 times B, without having a longer element in my Weil group. If I was looking at F3, then instead of having 3 branches at everything, I would have 4 branches, and in general, it'd be Q plus 1 branches if I'm looking over FQ. So this generalizes further out. I could also do this over C, and then I would have C many branches, C plus 1 many branches at every point, but I definitely can't draw that. So we'll look at F2. Yeah. Okay, so these come up over here, and something like this, you know, would give me a finite building. I also have infinite buildings when I'm looking at the theory of affine flag varieties, which again, I'm not going to formally define, but I am going to sort of explain in the guise of these examples. And if you're familiar with affine flag varieties, then this kind of construction can be repeated all through with buildings. So in this case, I'm looking at SL2, the special linear group of 2 by 2 matrices, over this field, which is the field of Laurent series with coefficients in F2. I have a valuation ring here, which in our case is power series over F2. So I've left off all the negative power terms in my series. And then I is an Eva-Hori subgroup. And you can generalize this in a variety of ways. But for me, it really refers to this kind of matrix. This is basically looking at my lower triangular matrices and then taking the pre-image of those in O, the valuation ring under the map T goes to T equals 0. So if I set this equal to 0, I'd be looking at lower triangular matrices is really the idea here. These things can be more precisely defined, but I think that's going to take us a little bit far afield. What I need in the building again is sort of, this is the stabilizer or something that is represented here. And then everything else in G, all my other cosets here, give me my affine flag variety, and I have a very similar decomposition to what I had with the Bruja decomposition. So right now I'm just describing what is in the blue box. I'll get to the red box later. But in this case, I'm looking at cosets of I. That is how I'm marking my edges, my top dimensional simplices. And in general, my Iwahori subgroups are going to do this. They're going to label each of my top dimensional simplices. The way I decide adjacency is deciding which double coset I'm moving to over here, which Coxeter group element takes me from one to the other. So here S1 and S0 are going to generate a Coxeter group that is going to be of one of the types we've seen before, giving me the infinite line. So again, over here, I have my infinite line, but I also have more branchiness that comes from being able to multiply in front by elements in my Iwahori subgroup. So this is sort of the setting over here. On the other side, I want to sort of briefly mention that one of the other things that we consider is the affine Grassmannian, which is in the building universe, in the setting that I'm in with these pictures, looking at what is happening to the red vertices. So this K I'm thinking of as a stabilizer under this action by G on the building of the red vertices. And the reason I care about the red vertices is because these essentially are built out of looking at the finite Coxeter group living inside the affine extension. So by W0, I mean all the, the subdiagram of my Coxeter group that comes from ignoring my last vertex that I added labeled 0, looking at the finite via group inside. So here I'm just left with one thing over here, a Coxeter group that's generated by one generator, and that is really where I'm looking at K. But more broadly, if you're not used to thinking about affine flag varieties and affine Grassmannians, you don't need to worry about the technicalities over here. Really, what we're looking at are edge labels and cosets of these, and then also vertex labels, which I can move in a similar fashion by multiplying by elements in my vial group. Okay, so that's the philosophy behind this. And now I come to sort of what kinds of questions I'm trying to answer. So these things I want to be able to study algebraically, and I want to think about what kinds of intersections I have between double cosets. So my main question here is, if I look at one of these cells over here indexed by some element X, and I look at the intersection with a different orbit produced by some other subgroup H, what kinds of things do I see? So I can ask the same question within like the affine flag variety and the affine Grassmannian. I can also ask this for partial affine flag varieties, and in fact, what we'll do later will answer both of these things. But this is the kind of thing that the connection between these two is going to try to answer, and what we are going to try to use the geometry of buildings to think about. So we're going to, like I said, try answering these questions about what these kinds of intersections look like as a way of thinking about how G acts on the set of cosets here in the affine flag variety and in the affine Grassmannian. And so this is essentially a way of tracing our orbits. And I'll say a little bit more about what kinds of H's people are interested in. But I want to talk about how the folded galleries connect to the buildings first. So the reason these two things relate, and the reason that we would have this kind of connection between them and get these foldings, is by looking at retractions of the building onto a single apartment. So if I fix an apartment, maybe I'll call it X. Sorry, I fix an alcove X, and I'm going to fix an apartment that contains X. So now I've outlined an apartment. Then I can think about the entire building folding on to this apartment here by doing the sort of thing that I was doing with the isomorphisms, which is I'll put both my hands at X, and then I'll just smooth over around this hexagon over here. So I start at X and I push outwards, and this means that this edge would collapse here, and all the subsequent edges would just collapse wherever they go. Similarly, on this side, this would get pushed out over here. And maybe it's a little bit easier to see here. If I have X and I have this infinite line, then I could think about putting my hands at X and smoothing out this way and smoothing out the other way. So all of these branches will collapse down over here. All of these branches will collapse down over here. But because I started with my hands at X, this branch would get swept over to the other side and collapse this way. Yeah. And what this does is it leads to any gallery that I've drawn. So if I have a gallery that was going, maybe this way over here, then this gallery ends up getting folded and moved around to the other side. So my old gallery picture, which is basically a sequence of alcoves, now I'm thinking of as a sequence of alcoves in the building, would get swept over here. And in the end, I would be left with a Coxeter complex, a single apartment, and I'd be left with a folded gallery inside it, which came from having a straightened out gallery in the bigger building that led me to some coset that I cared about and got pushed down, just leaving me with the final image. And now the way I decide what kinds of folds I'd have would really be folds away from this alcove X, because I started with my hands there and started pushing things away. So what I get is this alcove-induced orientation where I could maybe put plus signs every time I'm away from X and negative signs every time I'm looking towards X. And so then the kinds of folds that I would see would all end up folding me away from X over here. Yeah. So these would be positively folded galleries with respect to a certain orientation. Okay. Now,
one question. If
yes.
you go back to the previous, so this works only over F2. If we are over F3 and things like that, the bifurcation will be bigger. And
so with, yes, F3, I would have more of these branches, but again, all of the branches would collapse the other way.
No, they will all collapse this way, but the gallery will, the information that we get from the folded gallery will not be enough to recover the original gallery.
It won't be enough, but it will only give me folded galleries with a certain kind of folding being allowed. Yes. We would need to actually keep track of which branch we were on as an extra parameter C.
Yes.
You do lose information in the folding.
Okay.
But all the folded galleries that you would get this way, regardless of which branches they were on, no matter how much the folding is, would be positive with respect to this orientation.
So in general, we could put some kind of weighted folded gallery.
Yes, you could put an extra parameter C that keeps track of these things. And then this C would basically be indexed by over here, F2. So I have like a 0 branch and a 1 branch, and I get this information. Or I could, if I had more, like if I had F3, it'd be 0, 1, 2. If I had C many things, then C would, then I could just keep track of a complex number parameter.
Okay, thank you.
Yeah. Okay, and so really, if I want to look at intersections of these double cosets, and I'm going to use this notation for conjugates just to compress it a little bit, this actually tells me when these intersections are non-zero. I only have a non-zero intersection if I had a way of getting through the building to something in a specific orbit, but it's hard for me to draw a full building, especially when I get to higher rank. It is easier for me to figure out when I can fold these things. So here's a theorem that I think goes back to Bruhatitz, who developed the theory of buildings. This kind of intersection would be non-empty if and only if there exists a positively folded gallery with respect to an orientation away from this of type X ending at Z. What do I mean by that? So I want my orientation to still be positive away from Y on each of these panels and negative towards Y. And then I just repeat this. So if I look at this panel, I want to put a positive away from Y and then a negative towards this. Like I have a little sun here, and then the shadows fall on the other side, and that's where I put my positive signs. So in this case, I have a negative on this side, a positive on this side, and I can fold my gallery away over here, going from a gallery that went from 1 to X to be a gallery of the same type, hitting the same types of panels, but now leading me to Z. So in this example here, I would actually have a non-empty intersection between these guys. If I wanted to keep track of which points were in the intersection, I would need the extra parameters of how much branching I had at this panel. But to just determine whether this is non-empty or not, it's enough to determine the existence of a folded gallery. But I would have a bijection with points if I kept the extra parameter. Now I can do a more complicated thing where I want to look at retractions from infinity, where U I'm going to take to be a unipotent subgroup inside my set of upper triangular matrices. So this has ones on the diagonals, and I think of this as upper triangular in this example. But if you're good with thinking about the Borel subgroups and the unipotent subgroups, these have generalizations. And I can ask the same kind of question about intersections over here. But now my subgroup H, instead of being this conjugate of my Iwahori subgroup, is this unipotent subgroup. And again, by looking at what these U's stabilize inside the building, I have this correspondence. The first correspondence due to Gaussant-Littleman, and the second correspondence due to Parkinson, Ram, and Christoph Schwe, where essentially I can look at a positively folded gallery of a certain type. The type that I want to keep is always the type from my starting gallery X. The orientation that I care about here is now an orientation that sort of comes from infinity in one of my 6 hexagonal directions. So remember that I said that we have this finite Coxeter group living inside my affine one. If I look at the longest element here, this is my CW0, and this sort of captures this freedom of having all the upper triangular matrices here. In this picture, I want to imagine the sun living over here, and then I put my positive sides on, I put my positives on the side of the panel away from the sun and negatives towards it. So positive away, negative towards it, positive away, negative towards it, positive away, negative towards it. And now in this case, I actually can't fold over to Z because this would be a negative fold. I don't have something that is positive with respect to this orientation. And so these kinds of intersections would be empty in this case because I don't have an allowable fold on the positive side. You can also sort of extend this out further in a very systematic way. But in this case, I'm going to get an empty intersection. Yeah, so these are the kinds of subgroups that I want to look at. Now, actually what I want to do now is look at something that lives in between them. So I'm going to go through this again, sort of quickly, but just to give you an idea of the kinds of subgroups we care about. I can interpolate between the Iwahori subgroup and these unipotent subgroups by considering these groups called IP, which were defined by Gertz, Haynes, Kottwitz, and Royman, or at least they use this heavily when talking about affine delinguistic varieties. And the way that I develop P, I can do quite formally. I'm not going to go through all this formalism here, but within the affine Coxeter group, I have this finite Coxeter subgroup that I get by leaving off my vertex labeled 0 in the Coxeter diagram. And within that, I can take a smaller subgroup that I would call Wj in this case. And Wj is going to consist, well, I can look at all the elements in this Wj, special subgroup of the Coxeter group, and look at what I get by just looking at cells associated to this. This allows me to construct a group But really all I need to remember from this IP is that this IP is associated to some subset of Weil group elements. I'll talk about what this means geometrically in our buildings picture in more detail, and that's a bit I want to focus on. But basically, the reason I say it interpolates between them is that if J is completely empty, so I don't have anything at all, I don't circle anything in red, I would basically get my unipotent subgroup back with some diagonal elements multiplying it. And if I take J to be everything, then I get my Iwahori subgroup back. But really, I want to reformulate my question in asking about what these things look like, where H is this IP, these kinds of in-between sets between I and U, and also I want to be able to conjugate them by Y. So remember that that superscript Y meant conjugating by Y. So these are the kinds of intersections that I want to give about. My co-authors were motivated, again, by applications to affine delistic varieties. But what I'm going to talk about here really just uses the geometry of the buildings, the simplicial complexes that we're looking at. And has a very combinatorial sort of description. Okay, so to define the geometric structure and the orientation I get to answer this question that I was looking at, this question in particular. So what is the orientation that goes with this IP when we've looked at orientations that go with U and with I? This was in alcove 1, this was from infinity. In order to describe those, I want to think about my spherical roots. If you're good with root systems, this is the ordinary set of roots that go with my Coxeter system. If you're not good with these are really just half spaces determined by the reflection hyperplanes, and this would work, this point of view would work equivalently well. So I could write out my roots alpha and beta as sort of half spaces on one side of these blue and red hyperplanes. Now this I would call H beta 0, because if I look at this direction beta, I'm making it product of 0 with them. I could also start labeling further out in this direction. So I would call this H beta 1. I'm still mainly looking at this half space, but I've shifted over by 1 over here. I could have H alpha 1 moving in the direction of alpha and H alpha minus 1 moving in the direction away. And then just adding these roots up, I get alpha plus beta, adding them as vectors. Okay, so each of these is going to give me some sort of, each of these hyperplanes gives me some affine root on one side, and then I have negatives of it on the other side. And so the orientation that I want, going back to the fact that each of my P's over here comes from some sort of subset inside the Weil group, means I'm looking at some sort of subset of these roots. I can use this to define a P sector. So I have a few definitions here, but again, the picture to keep in mind is when I look at the things that go into my WJ, so supposing I just have things generated by the, red reflections over here, I'd look at my red root alpha. I would look at the region between H alpha and H alpha 1 for the roots that I want to select into my J. So I would be looking at regions between H alpha and H alpha 1 over here. And then I would actually be moving in the negative beta direction, or really in the negative direction for all the other roots. So I want to move away from 1 relative to the directions beta and alpha plus beta in this case. And this is what gives me a PY sector. This is looking at the case where J or WJ is just going to be this thing labeled by 1, or J just consists of the first element over here. I could also do the same thing using the other direction beta over here. Oh, sorry. And that would give me some sort of sector. In this case, if I looked at a situation where J is taken to be 1 and 2, so I'm going to go back. Sorry if this is a bit dizzying. If I look at the case where J consists of all my indices 1 and 2 living inside W0, then I would end up with this whole situation over here. Oh, sorry, the J is empty case over here. And the J is everything case would just give me an alcove over here between the 1 and -1 things. So the reason this interpolates is because if I take one thing, I get something that's sort of constrained in one direction and infinite in the other direction. I might have something that's constrained in all directions, and that just gives me a single alcove, or I might have it constrained in no directions and going off to infinity in both the alpha and beta directions, going to negative infinity. My Py is the limit of these Py sectors, and then I can use this to define an orientation by marking a little sun over here, and then putting positives away from it, negatives here. And then also I want to have positives away from it on each of the hyperplanes in this direction. So this is looking at the sun over here. So I have an orientation in this case. Okay, and now this orientation that's induced by the Py chimneys actually completely answers the questions for when I have points, or when this intersection here is non-empty. I might want to translate it by y if I'm conjugating by y, so translate this chimney over by left multiplication, but each of these points in the intersection is labeled by some positively folded galleries, and the labeling here would be exactly these extra folding parameters. I was going to give an idea of how you prove this. Let me actually just write down my full reveal of the idea of proof, but in the interest of time, I think I may have to skip this over. The way that you would prove this and show this association is basically by considering the different types of roots you have, the ones that are associated to the parabolic subgroup indexing P and the ones that aren't. If they are, you can just use this kind of alcove orientation, and if they aren't, then you could essentially generalize from the infinity orientation using this kind of strategy that Parkinson, Ram, and Christoph Schwer actually used in their paper when they were dealing with the unipotent subgroups. So this kind of equation comes up in their work also. But like I said, this is something that can be proved out completely formally. I want to get to how we compute this. And before I sort of mention how we compute this, let me just sort of specify that computationally this can get quite messy. So the thing that I stated earlier was—
Can I ask a quick question?
Yes.
Before you start. So I'm just sort of trying, can you go to previous slide?
Yes.
So here in the theorem, you meant to say there exists positively folded
Yeah,
label.
so really this one is saying that they are in bijection.
Points of intersection.
Yeah, so the points, these are really G mod I points, are in bijection with the positively folded labeled galleries, but here I need to keep track of a parameter.
But isn't there sort of more than one way to take a gallery to a given, like,
yes, and these turn out to be braid invariant, so as long as you fixed a type for X, it doesn't matter which one you take.
So when you say in bijection, are they in bijection with braid equivalence types of those, or just with single galleries?
Once you fixed a type, I need to just stick to that type. So I have picked a certain reduced word.
No, I don't understand. You have a beginning point X and an ending point Z. And you you're considering positively folded galleries which go from X to Z. Isn't that right?
I'm going from 1 to X, and that fixes a type based on the kinds of panels that I cross.
Okay.
And then I want other galleries that have the same type, so cross the same sort of panel, but end up at Z. So Z is going to be typically a shorter word than X.
I see, I understand.
Yeah.
So
now I'm going from 1 to Z over here, but I'm crossing the same types of panels.
So, and for example, if this is happening over finite fields, it means that there's only finite, I guess then everything is finite.
But really what I have to do is keep track of the parameters at every fold. So these extra little pieces of information, C at every fold. Here, I just need one parameter. But in general, this has as many options as there are in my field. This could be a finite number of parameters possible for the labeling, or it could be infinitely many possible for the labeling.
But, so one more thing, just last thing I'm trying to understand. So it sounds like you almost insist on folding. Like, can't those galleries just be without folding?
Yes. Like, so if I don't fold, then all of the parameters can still label it. If I do have a fold, I can, because of the way the proof would go, I actually need the non-zero elements folding it. Parameters, so the labeling is complicated, and I am brushing some details under the rug because I sort of, it was in service of, here is a nice picture. You could keep in mind.
I think, yeah.
But
okay,
I don't want to make it
even if the original gallery towards X is not folded, when you go to Z, you may choose to fold.
Yes. So in order to get to Z, so my X and Z are going to be given to me by the problem of searching for the intersection.
Right.
And then I want to think, can I get to Z using things of the type X? X is going to have a minimal gallery, no folds. In order to get to Z, I will have to fold someplace, or I'm never going to move from X. Right? And so then the question is, can I do this with positive folds?
I see. Okay, I understand.
Yeah. And so you can make an existence question where you don't keep track of parameters and you're just saying, is there one possible way? And then it is an existence statement. And if I'm looking at partial flag varieties, then actually an existence statement is much easier to make. So in the case of the Grassmannian, which is what I have this picture drawn for, I have made this an existence statement because it's harder to keep track of the bijection of points in this case, because now a lot more happens with those actual labelings. And so I was going to focus on this picture, but the theorem that we have is actually a little bit more general in the case of looking at the full affine flag variety. Or yeah, it gives you more information in the case of the full affine flag variety. But otherwise we can still make an existence statement over here that says that this kind of intersection would be non-zero if there exists something that is positively folded with respect to the chimney orientation. And so here in this case, I have a minimal gallery X, and now I'm not keeping track of labelings and the parameters at every fold. I'm just asking, does one exist? Because it's harder to get bijections. And so this chimney over here, this is a little sector and I've moved it back. This is what I mean about taking the limit. I want to be able, so really once I start with this type X, in the case of going from vertex to vertex galleries, I actually have I have many more starting points that have the same type. I really take the finite Weil group orbit of this X, and then I think about all possible folds of these guys, where really the only allowable folds are away from this chimney. So I can fold upwards away from it, but I just can't fold inwards. If I just move this slightly, so I translate by Y to the side, it does allow a few more options. But in general, finding out what all of these things are and even getting a non-emptiness comment is computationally difficult. And so the next thing that I wanted to talk about was sort of our computational result. Sorry, was there a question?
Sorry, my microphone was on.
Okay. So what I want to do is determine when I have a gallery of specified type. So what I'm looking for is the shadow of a gallery with respect to an orientation. And I'm going to define this to be the points I can hit by using a gallery of a certain type that is positively folded with respect to an orientation. And I want to be able to do this for my chimney orientation in particular, but there's a broader question here of what these shadows would look like, which is really which endpoints do I get when I fix a type of a gallery and insist that I only have a certain kind of fold. And here's an example to show you that if I'm just folding galleries by hand, it really is quite complicated. There are a lot of hyperplanes to consider and all of the induced orientations that we would need to think about. But one of the nice things about PY chimneys is that each of these can be produced by using an alcove that is sufficiently far away. So these chimneys I think of as going out infinitely long, but if I have a fixed starting point, so if I have a gallery that goes out to a certain place, then for that gallery, I can approximate that chimney orientation by looking at an alcove orientation using an alcove that's sufficiently far away. And so now I have a question about alcove orientations. And so let me actually just get to our main theorem, which is a recursion on what kinds of endpoints we would hit using this kind of alcove orientation. The alcoves, remember, are indexed by elements in my Coxeter group, and my Coxeter group elements have length. And so every time I'm looking at the shadow with respect to an orientation produced by an alcove, I could use that information to get the shadow with respect to an alcove that is further away by taking my previous shadow and adding in some more points. So if I have a set of points that come from the shadow due to X, then in order to figure out what the shadow is due to this alcove that's further away, I would keep the same elements, but then I would also reflect in, so maybe I should have drawn this a little bit better. So if this was further out over here, I would get new elements coming from just reflecting the elements that are further away from X back over. So I look at things on the side of the hyperplane that's closer to XS than to X, and I would reflect them over. So things that were in the old shadow, and this gives me my new point. So it allows me to build this up iteratively. And the way I would use this is really I would look at a shadow with respect to a certain alcove over here, X. Right now, this doesn't actually let me fold because it's insisting that I keep everything moved away. But remember that in the alcove, in the vertex to vertex type, all of these have the same type. Then if I want to think about the shadow with respect to this, I take each of the things that were on the far side of the green hyperplane and reflect them over. And this gives me a new set of endpoints. And so this is a nice, remarkably simple recursion. I should say that it's not actually true at the level of galleries. And the hard part is I'm saying that I get these new points which would be positively folded because I'm moving them away from XS. And that's all well and good for this part. The shadow of the old thing, the fact that I can keep all these old black points that I had is actually the trickier part over here, because a positively folded gallery with respect to X is not necessarily positively folded with respect to XS anymore. But there is a modification and a bijection that is possible to use in each of these cases, which really means that this recursion gives us a nice way of computing what kinds of things I get, what kinds of end alcoves and vertices I get when I want to use this kind of orientation coming from infinity, as long as I have like a stable alcove. And so here are just two examples where you can see that I have bypassed having to take a gallery and think about all the folds, especially because there's multiple folds and multiple parameters that would get me to each of these. But as far as intersections being non-empty, I can compute these for alcove to alcove galleries, vertex to vertex galleries. Really, I can also do edge to alcove galleries, alcove to edge galleries, all sorts of things, which is why this formalism works for partial affine flag varieties as well. But now the recursion is pretty simple. I just look at the kinds of hyperplanes that I would cross going further and further away in my chimney until this stabilizes. And each time I'm just reflecting over the things that I have, keeping old points. Here I've marked all the things that I get to reflect. And this is actually pretty easy to program and automate for all initial starting types, as long as I have a way of encoding my initial root system and describing the chimney. So this suddenly makes computing the intersections of these, instead of big problems about matrices and cosets and various points, a nice non-intersection problem that uses this recursion, using the fact that the buildings and the geometry tell us quite a bit. That is where I'll stop. Sorry for going a little bit extra long.
All right, let's thank the speaker.
Oh. Yeah, so many people.
So many people. Are there any questions for Yusra?
I actually have two questions, but
go for it, Nantal. That'll give people time to formulate their questions.
Yes. My first question is a bit crazy thing. Is you know, like when you were talking about you have an orientation where you have plus and minus, and you just bounce off the pluses. For some reason, I was wondering if it would make any sense to anytime you would allow to cross some negative, but an even number of times. What does that would it compute something interesting as well? Now you're computing intersection, but what if you were to allow crossing negative, but an even number of time, a little bit like a
yeah. So I don't know if crossing negatively in even number of times would have meaning in this setting coming from retractions, but there are many circumstances in which people do care about allowing negative folds as well, because they're keeping track of, so not for intersection type questions, but a lot of these kind of folded galleries and these sorts of things going with the things labeled by the affine Grassmannian. I can index these with monomials, and in symmetric function theory, people do care about the negative folds and the positive folds and just keep track of extra parameters for how this is modifying something moving around in the larger Grassmannian, because these were all also points that live in there. And sometimes we want to throw them away because we're saying they're not in our sets, but sometimes we want to keep it and they just pick an extra weight of a different sort for how we're combining these things.
That's great. And yeah, it answered what I had in mind. And a second thing, a more nasty question is, so why do we care about those intersections? What do we do with that?
So those intersections, yes, okay, so those particular intersections, like I said, were sort of motivated by my co-author's work with affine Deligne-Lustig varieties and trying to find non-emptiness patterns and dimension formula for those. I don't actually work with the affine Deligne-Lustig varieties myself, but these are basically, I think, of importance from a representation theoretic point of view.
Okay. So like a really little bit like the dimension of these things would be giving us invariant about some representation or something like that? Or?
Yes. And I mean, the action that you have here is the group G acting on these affine flag varieties and how it's moving the cosets and stuff around. So there is a very nice action there, and there's a nice action on buildings and stuff. The dimension formula that they're looking for and what they sort of are working with in general, I think, is sort of more specific to the theory over there, which I couldn't tell you very much about. But the way I came at this was some of this from the geometric group theory point of view. The other thing is, you know, you can get, for instance, character formulas for De Major models and stuff, also using these sort of folded galleries and everything by indexing, you know, points in the affine Grassmannian and looking at monomials over there. So the question of what multiplicity of these galleries do you have? Which kinds of galleries do you want to keep in order to do these computations? Do you keep all of them? Do you impose extra restrictions? Is sort of where I come into this. But the IPs in particular sort of have a very natural sort of interpolation between two sort of sets that people cared about. So that was setting some of the stage. The ultimate thing with both of them is that they, in the end, if you're just reducing it to a question about the orientations, you can't just really look at alcove orientations. So in some sense, I maybe could have skipped over a lot of that and just spoken about alcove orientations.
Okay, thank you so much.
Can I ask a quick question?
Yes.
So those orientations of plus, minus, they remind me very much inversion sets of affine permutations. Is there direct connection? In particular, there is a way to also talk about kind of infinite inversion sets, like so the technical term would be biconvex sets.
Yes. So I believe that this would give you, okay, so I believe these are related, but I probably could not tell you very quickly what the relation is, sorry.
Maybe I'll email you and then ask you about it.
Are there any other questions? If not, we'll thank the speaker again. And I guess we'll see each other in 2 weeks' time, since next week is Thanksgiving.
Yes.
Thank you, Yusra.
Thank you. It was a very nice talk.